Hello and welcome back. So what I want to do today is finish working on my LISN, something that I started working on a while back. So make sure to check out those videos before this one. So what I want to do today is look at what are the problems with this thing, what are its limitations, and well, try to fix them. And the main thing that I want to focus on today is trying to improve the interchannel isolation. So the signal that goes from one channel to the other. Now, lately I've looked at the various concepts behind magnetic and electric field shielding, and well, today is a good chance to apply those. So if you're curious about that and much more, then keep watching. So let's start things off by looking at some of the problems that the initial design has. So the first and the most obvious problem was that the 5 microhenry LISN doesn't have 5 microhenry. It has a bit more. We can see this when we look at the graph of the output impedance and comparing this to a graph of what it should look like. And what we could see was that our measured impedance was slightly shifted to the left than the ideal graph would indicate. And that can only happen if we have more than 5 microhenry in our main inductor. And well, fixing this is not that difficult. I need fewer turns on my coil. But because of the way that the inductor was built, well, it's easier to just make a new inductor than to try to fix the already built one. So I ended up building a new inductor and well, a new circuit, but we'll get back to that in a moment. Now the next thing to consider is the supply line filtration. Now, even though there's no specific requirement for this, there's no standard that dictates just how much filtration you need from the supply line side, and especially if you're using a battery to supply your circuit through the LISN, then well, you don't really care about any filtration because there's not going to be any noise coming from the battery. But on the other hand, if you're going to supply your circuits from a DC-DC converter, so I will most likely be using some sort of power supply plugged into the mains, then isolation from the supply side is something that you would want. And what I want to do about this is to change this inductor to 100 microhenry. And this should improve the filtration capabilities. And well, I had a 100 microhenry inductor lying around, so I'll be using it for this occasion. Now, there's one more thing that I want to change, and that is this signal coupling capacitor. So in the previous design, I used an 100 nanofarad ceramic in parallel with a 10 nanofarad ceramic. And what I want to do about this is to change from a ceramic capacitor to a film capacitor. The main reason to do this is to have a far more stable capacity. Now, for most ceramic capacitors nowadays above, well, roughly 10 nanofarads, you will be working with class 2 dielectrics. And one of the problems associated with this type of capacitor is its DC bias characteristic. So what I have here is a random 100 nanofarad capacitor, and one of the graphs associated with this is this derating that is applied depending on how much voltage is applied to the capacitor. Now, I don't want to go into too much detail on this, but capacitors have a similar behavior to inductors with magnetic cores. They saturate. So the higher the voltage that is applied, the smaller the capacity that you end up getting. So one of the things that the capacity is strongly dependent on in class 2 dielectrics is the supply voltage. And with film capacitors, this effect does not exist. So for this reason, the film capacitor will be a far more stable capacity. Finally, it's time to tackle the big issue, the interchannel isolation. So last time we saw that we had this V shape in the noise. So channel isolation was increasing up until a point and then it was decreasing again. So how does that work? Well, some viewers suggested that my magnetic field shielding around the coils isn't really working. So is this a magnetic field issue? Let's check this in the simulation. So what I got here is a simulation of the two channels of the LISN with a signal source connected to one channel and with a measurement port on the other one. So if we run this simulation with no coupling in between the two channels, and we look at the output of the second channel, well, there's no coupling. And this is what we would ideally want. But now, if we provide a bit of coupling, so magnetic coupling, for this I created a transformer in between the two 5 microhenry inductors with a coupling factor of 10%. And if we rerun this simulation, we can see that on the second channel, we get this bell shape. So we see that coupling is increasing up until a point, and then it's decreasing. And this inflection point is happening around 1 MHz. Now, we can explain this on the one side, because the transformer is coupling more energy as frequency increases, so that's why you have a rising slope. And then for the falling slope, well, current no longer goes through the inductor, but rather it starts going through the capacitor into the 50 ohm termination. So as frequency increases, the impedance of the inductor also increases while the capacitor decreases, so current will go through the path of least impedance, through the capacitor. And hence we get this bell shape. Now, if we look back at our initial measurement and we try to compare the two graphs, we see that our coupling is decreasing, so even beyond this 1 MHz point, but then it starts to increase. So strictly speaking about magnetic coupling, the only part of our coupling that could be explained by magnetic coupling is this initial slope. The thing on the right has some other cause. But before looking at that, let's first confirm our initial magnetic field coupling. So let's start off by looking at the previously built magnetic shielding. So the shielding is this copper band that goes all around the inductors, and the way that this works is the same way that the flux band works. So I covered this in an older video. Basically, it's a single turn that's short-circuiting any sort of magnetic field that would want to escape it. So to see just how well it actually works, first let's remeasure a baseline and then try to interrupt our flux band. So our first measurement is the signal passing through the LISN, injected on one channel and measured on the second one. And well, it's the same measurement that we've seen before, it's just that it's not processed. But we can make out this bump here, which is our magnetic coupling. So, or at least what we've seen in the simulation as being magnetic coupling. So next, I will be cutting my flux band. So I'm not removing it, it will still stay on the inductor, it will just be interrupted. So if we remeasure like this, we can see that our high frequency behavior is roughly the same, but our bump has slightly increased. Now at the moment I just cut the flux band around our receiving inductor, but I will do the same thing on the other inductor now. So now the shielding in the second inductor also has a cut, and if we remeasure, we can see a substantial increase in coupling. So even though this sort of shielding isn't perfect, it's better than nothing. But regardless, for my final design, other than the copper band used as a flux band, I will also be using some ferrite sheet to provide some magnetically permeable material around the coils for some extra shielding. Now it's time to tackle the high frequency noise, which is a bit more difficult to analyze and to, well, understand. So first, let's go back to the simulation. So as confirmed by our previous measurements, the low frequency noise passes through the inductor, which at a certain point starts to drop down. So the current going through the inductor, which is coupling magnetically, starts to die down after a certain point in frequency. So the signal coming into the LISN goes somewhere else, namely this signal coupling capacitor. So as current dies down through the inductor, current goes up through the capacitor. So at high frequencies, the part of the circuit that we will be interested in will be the loop formed between the signal generator coming in through the capacitor and closing down into the termination resistor. This part of the circuit will be of interest because, well, this is where the high frequency signal goes. It doesn't really go into the rest of the circuit. And to see exactly where this goes, let's now look at the actual circuit construction. So this is a close-up picture of the LISN. We've got our signal coming in through the BNC connector, going onto the small PCB through the coupling capacitors, and then through this coax cable goes down into the termination resistor. Now, the signal doesn't just stop there. It needs to close back through the ground back into the signal generator. And now this is where it becomes a bit tricky, because the ground connection to the signal generator is coming through the small wire here on the backside of the metal casing. So the signal going to the termination needs to somehow get back into this point. So from the termination, it can either go directly through the case, it can go through this shielding on the coax cable and then back down through some other point, go through this support stud. So there's a metal stud here that is holding this whole structure up. So there's a lot of paths that the high frequency current can go through. And well, all of these are quite high impedance and they're forming quite large loops with the initial signal path. So they're all causing part of the problem, because this huge loop can radiate both magnetic fields and electric fields. And well, the secondary side of the LISN is not at all protected from this noise. The ground is quite common, so through the enclosure, and the two signal lines are both exposed, so electric fields can pass from one to the other. Now, to fix this, there's two main measures I tried out. So first of all, since there's no proper ground connection in between the two structures, so the metal casing and the PCB, something that's close to the signal lines, first thing I did was add this copper wire that creates a much shorter path to the metal case. And well, when measuring this, here I just overlapped an initial reference measurement in pink and in white this measurement with the added wire. We can see that here in the middle, where we have our magnetic field coupling, nothing changed, so this has no effect on the magnetic field coupling, which is caused by the inductors. But we can see that at high frequencies, the noise coupling starts to go down. So by bringing the ground of the small PCB to a closer potential of the metal casing, we can see that the coupling starts to reduce. So we're on the right path. Next, to try to improve on this, so reduce the impedance between the 2 points even more, and at the same time prevent the electric fields from jumping from one of these terminals to the other, what I did was add a big piece of PCB that will act both as a connection point and as an electric field shield to isolate the two channels of the LISN. And now if we look at how this affected our measurement, here I have the two previous measurements, so the pink and the white one, and in blue we can see the measurement with this added piece of PCB. So again, magnetic field isolation was unaffected. This only had an effect on the high frequency noise. And we can see that all around we had a reduction in the high frequency coupling in between the two channels. So the main problem with the high frequency noise is coming from potential differences between the structures inside of the LISN and from electric field shielding and, well, the lack of it. So by properly separating the two channels, properly shielding one from the other, on the one side for magnetic fields at the coils and on the other side for electric fields closer to the terminals, we should be able to get a far better isolation coefficient in between the two channels. So now we have all of the information needed to improve on the initial LISN design. Let's see how the new one works. Now, the building process went smoothly, but the circuit didn't really work well the first time. So I have two sets of measurements, but this will help us give more insight into how such a basic circuit can be negatively affected by seemingly good measures. So first, I will go over the constructive details of the two versions, then we will look at the results. So this is what the inside of the thing looks like, with our magnetic shielding being applied, so the extra ferrite sheet on top of the already existing copper foil. Then here on the right side I have the wall built, so again built out of a piece of PCB, closely connected to the ground of the PCB and to the casing, and then also the ground of the other PCB, so the one with the input side filters, is also connected to ground with a copper strap. And then, other than these measures used for isolating one channel from the other, what I also added were these film capacitors, which are on the bottom of the first PCB. So these are located here just below this PCB, they're not visible in this picture. And well, I also added these large 100 microhenry inductors on the first PCB. So this is on the input side to filter the input supply line. Now in the second version of the circuit, I changed two things. So on the one side, I removed the film capacitors and replaced them with a bunch of small ceramic capacitors. So rather than relying on a film capacitor to have a stable capacity over a wide voltage range, I added 10 pieces of 10 nanofarad capacitors, which will also exhibit a much smaller capacity variation with the applied voltage. And the second thing I changed were the 100 microhenry inductors back into the old 10 microhenry inductors that we had with the first circuit. So now let's see why I did these things. So I don't want to go into the details of how the measurements were made. These were made exactly the same way as in the previous video, so go check that out if you're curious about how the setup was constructed. Today I will only be focusing on the results obtained. So the first thing to look at is the output impedance. So what we've seen last time, so we have here the old LISN measurement, the line in green, was that this measurement was shifted to the left. So we had a bit more than 5 microhenry. Now by removing a couple turns in both of my measurements, so the first construction of the LISN with the film capacitors and the 100 microhenry inductors at the beginning, as well as the second construction, the one with the ceramic capacitors and the 10 microhenry at the beginning, we see the impedance was shifted to the right. So we have a smaller inductor this time than with the previous measurement, so the graph is closer to what it should be. Now, other than this central area, we notice a few more things. So here at the beginning, in purple, so this is the case where we had the 100 microhenry inductor at the beginning, we see quite a large impedance, and well, this is not a good thing. So that's the main reason why I changed back to the 10 microhenry inductor. And in blue, we see the second measurement where our impedance again decreased. So to have a good low impedance at low frequencies, we don't really need the large input filter inductor. It's causing more problems than benefits. And then if we look at the high frequency area, we see this bump appearing. And now this was on the circuit that had the film capacitor as a signal coupling capacitor. And well, when I changed this out for the ceramic capacitor, this bump disappeared. So this is probably some sort of resonance appearing because of the larger series inductance of the film capacitor. And while going back to the ceramic, we get a much more flat response. Second thing to look at, the insertion loss, so how much of the signal coming in through the port of the LISN actually goes out through the measurement port. Here again we see in red our old measurement, and then in green the new measurement with the film capacitor and the 100 microhenry inductor. So here again we see this bump appearing, so the resonance caused by the film capacitor itself. And then when I swapped out the capacitor for ceramics, and well, got back to the old 10 microhenry inductor, we see that we have the exact same shape as with our initial measurement. Now the whole graph is slightly shifted lower, but this might be some sort of measurement error. But regardless, we have quite a flat insertion loss, so this parameter wasn't really affected by any of the measures. Next, the input side impedance. So this is the impedance of the LISN seen from the side from which you supply the thing. And we can see here again in red the old measurement, which was quite flat around 100 milliohms. And then the two new measurements both have this V shape. Now, come to think of it, the V shape isn't that much of a surprise. So the very first thing on the LISN input is a very large ceramic capacitor. So this sort of V-shaped impedance is quite normal. What is not really normal is the flat response we got last time. So either there was some imperfect contact increasing the resistance or some other issue with the setup, but this new V-shape is what we should be expecting. Other than that, we get roughly the same kind of impedance above 100 kHz. Now, another measurement which isn't really exactly what I would expect is the input noise filtration. So how much of the noise pushed into the supply input of the LISN is visible on the measurement port on the other side. So here in green we see our old measurement, in red we have the noise floor, so somehow the old measurement was below the noise floor, which is a bit odd. And then we see the two new measurements, so in blue the one where I had the 10 microhenry inductor, and in purple where I had the 100 microhenry inductor. So especially at low frequencies where this inductor matters, we can see that the 100 microhenry inductor provides more filtration than the 10 microhenry inductor. But as stated below, this parameter isn't really that important if your supply line isn't very noisy. Regardless, at higher frequencies, both the 10 and the 100 microhenry inductors provide the same amount of filtration, and for whatever reason the old LISN had more filtration capabilities, so less noise was passing through that one. But again, here I suspect some sort of measurement error. And finally, we reach the most important measurement. So how well the two channels are isolated one from the other. So when noise is injected into one of the channels, how much of that noise is being measured on the first channel. And here again we have in red the noise floor, in green the old measurement, so the one that's roughly at the same level as the noise floor up until 100 kilohertz. Then we have this V shape, so the one that we've seen that in the beginning is mainly caused by magnetic field coupling, and in the secondary side it's caused by electric field coupling. And here we see quite an interesting result. So when I had my 100 microhenry inductors, I had more magnetic coupling than before, so somehow even though I added the ferrite sheet to isolate the two 5 microhenry inductors, the result was even worse. When I went back to the 10 microhenry inductors, the result was roughly the same as before, maybe slightly smaller. And the main reason for this is the inductors themselves. So the inductors that I've used are unshielded inductors, meaning that any sort of magnetic field that they create, well, is free to escape into the environment around them. And because of the way these were placed onto the board, these two were quite strongly coupling in between them. So even though not a lot of signal was reaching these inductors, it was very strongly coupling in between the two channels, so we end up seeing quite a lot of magnetic field coupling, not because of the 5 microhenry inductors, so the main inductor in the LISN, but rather from these filter inductors. There might be a good reason why a normal LISN doesn't have this extra input filter. It may be causing more problems than benefits. But anyway, coming back to the second part of the graph, so where we have our high frequency noise coming from electric field coupling, we can see that in both cases we are better than with our old filtration. So the shielding wall that was built in between the two channels is providing valuable and useful isolation in between the two channels. So at least this part of the experiment went well. Now, there are a few things that we can learn from this. On the one side, if a device isn't supposed to be complicated, don't complicate it. It will just make it worse. Or at least I did. And secondly, there's probably a good reason why LISNs come in single channel versions. So not having both of the channels in the same box. This can be, of course, achieved with quite good results, but special isolation measures need to be applied. But in the end, the LISN that I've built turned out quite decently, so I will be leaving it as it is. I won't be making any more improvements on it, and hopefully in the near future I will be using it for some experiments. With that said, hope you got some useful information out of this. Leave your thoughts in the comments. Thank you for watching. Make sure to subscribe to be up to date with all my videos, and see you next time. Bye bye.